In this video, we are going to be discussing gravitational potential energy that corresponds to universal gravitation. Gravitational potential energy is an energy that an object possesses because of its position within a gravitational field. So far, we have defined gravitational potential energy for situations where you have some object of mass m that happens to be near the surface of the Earth, where the gravitational field strength is uniform. It means that the value of it, which is g, is equal to 9.8 newtons per kilogram, and it's always going in the same direction, which is straight down. You can notice that the field lines that are shown here are all equally spaced, hence it's constant, and they're all pointing in the same direction, which is down. If we were to calculate the force of gravity acting on this object, F sub g, we can calculate it simply by using this formula. The force of gravity equals the mass of the object multiplied by the gravitational field strength. The force of gravity is a vector. It would be pointing down in the same direction as the gravitational field. And we can calculate the gravitational potential energy change as this object falls downwards, losing gravitational potential energy. To calculate the change in gravitational potential energy, we would need to know the vertical height that it fell, shown as either h or delta y, the mass of the object, and also the gravitational field strength. The change in gravitational potential energy would be calculated by using delta U sub g is equal to mgh or y, delta y. However, this formula only works in situations where the gravitational field strength is constant, which is pretty much okay for most of the problems that we use near the surface of the Earth, because g is approximately 9.8 newtons per kilogram, and it's uniform and constant near the surface of the Earth. And that's what we've been using up until this point. But what about problems where you start to look at objects where they're moved further and further and further away from the surface of the Earth, like a rocket flying out into outer space? If you were to take this object that was near the surface of the Earth, you could find the gravitational potential energy simply using this formula. But if you put it and start moving it further and further away from the Earth, then the force of gravity gets smaller. The gravitational force acting on this mass is no longer constant as it was in this picture. You see, the force of gravity to be calculated between two objects with mass m, let's call that m1, and the planet m2, can be calculated using this formula over here, which is known as Newton's universal gravitational law. The force of attraction between the two bodies is directly proportional to the product of their masses and inversely proportional to the square of the distance separating these two bodies, from the center of this object to the center of the planet. And the gravitational field for this is not constant. It's going to be stronger here than it was over here. The further the spacing between the lines, the weaker the field. So as you bring the mass further and further away from the planet, the gravitational field strength is not constant. It's no longer, as it is over here, 9.8. It's going to get weaker and weaker and weaker. In fact, if you took this mass and moved it so far away into deep, deep outer space, then there would be no force of gravity acting on the object. It was infinitely far from any other mass. There would be no gravitational forces acting on it at all. So, as r approaches infinity, in this equation over here, the force of gravity will approach zero. So, it would make sense to set that gravitational potential energy to also be zero at an infinite distance away. If these two masses were infinitely far from each other, there would be no gravitational pull acting on them, and hence there would be no gravitational potential energy. So this equation over here, for calculating the change in gravitational potential energy, can only be utilized in the scenario shown to the right, where you need to know the height that it drops, and the constant gravitational field, and the mass of the object. But if you try to use this form over here, you can't, because g is no longer constant. The general equation for the gravitational potential energy of a system involving one mass, m1, and another mass, m2, is given by this equation over here. The gravitational energy, U sub g, is equal to the gravitational constant, times mass 1 times mass 2, divided by the distance. So it's directly proportional to the product of the masses and inversely proportional to the distance separating them. And this formula can be found on your AP Physics formula sheet. The value for g, by the way, is the universal gravitational constant, which is equal to 6.67 times 10 to the power negative 11 Newton meter squared all over kilogram squared. Now here comes the slightly confusing part for many students and even teachers, this negative sign that you see here. The gravitational energy that an object possesses is actually negative. It takes positive work to take this object that's way out here an infinite distance away and move it to a close location near the surface of a planet. The result of having these two objects near each other is a negative gravitational potential energy. You see, we decided earlier that at an infinite distance that the gravitational potential energy would be zero. We chose that simply because there'd be no gravitational pull, so there'd be really no gravitational potential energy in the system. We sometimes call that system unbound. The other mass wouldn't be gravitationally attracted to the other mass, so they'd be free to move and not bound to the other mass. But if you were to take one of the masses and move it so it's really close to the other object, then it would have this negative gravitational potential energy, and they would be bound together, pulling them towards one another. To make that object be free from the system, you have to give it enough positive energy so that it can escape and not be bound to the system anymore. Let me try to explain with a simulation. All right, I pulled up a simulation called My Solar System. It's from the PhET website here. You can download it for free. I've got one mass here, rather massive, with 200 units, and then I've got a small mass 1. So this could be like the Earth, and then I have some rocket that's firing it out into outer space. I'm trying to get the idea that this system has negative gravitational potential energy. And if I give this rocket enough kinetic energy, it could be unbound. Right now, with this velocity, if I press start here, you can see it fires away, but it slams right back into the Earth. So I need to give it a little bit more velocity. More velocity means more kinetic energy. And yeah, it's getting further away, but it's slamming back right into the Earth. So it has to have the right amount of kinetic energy so that when I fire it, it's going to continue moving away, further away from the Earth and never come back and basically be free. All right, back to our notes. So over here I've added a picture of a marble in a bowl. This might help you give an idea of what this negative gravitational potential energy is all about. Imagine I took this little marble and I gave it a bit of a tap and it would roll back and forth in the bottom of the bowl, but it still would be bound to this bowl system. However, if you were to give it a big enough tap, the marble might just get up to this side and then leap right out of the bowl, and then it would no longer be bound and it would be free. You see, the region around a mass, like a planet in outer space, it essentially warps the space-time around it and creates this gravitational field around it. Another visualization of this is this three-dimensional gravitational potential that you can see shown to the right. The planet would warp space-time around it, and you would see something three-dimensionally like this. So the Earth is kind of down here, and it's warping the space-time around it. And then this little red circle here would be like the marble or the body that you're trying to fire away from it. You would have to give it enough kinetic energy so that it could escape and not be bound to the system. Right now, if you were to just simply leave it at rest, it would fall into the potential well. So we have this negative gravitational potential energy, which is shown by this sinking well, and then you have to give it enough positive kinetic energy for it to escape this negative gravitational potential energy. In your chemistry class, you may have learned about the electron being bound to an atom at certain energy levels. Maybe you discussed energy level diagrams. Have you noticed that these energy levels are all negative? These are all negative potential energies because the electron is bound to the atom. Notice that ground state, which is the lowest level, does not have zero potential energy. It has an energy of negative 13.4 electron volts with respect to this point right in here, which is known as continuum. If you had an electron on a certain energy level, such as this one, n equals 2, you would have to give it enough kinetic energy so that it could basically become unbound to the atom. In this particular case, you would have to give it exactly positive 3.4 electron volts. If you give it any value less than that in positive energy, it will still be bound to the atom. Okay, so I spent a lot of time trying to explain the negative in this equation. Hopefully, you're not more confused. So, in summary, we want to calculate the gravitational potential energy of two bodies, such as a rocket being fired away from the Earth and the Earth, so the rocket Earth system. You could calculate it by using this equation, g times m1 times m2, all over the distance that separates them. And there's a negative there. Okay, so for those of you guys who are not in calculus, you could start working on problem solving. If you are taking calculus, you might be interested in the last few minutes of this video, in which I'm going to derive this equation using calculus. So let's suppose that you have some mass here, we'll call that big M for the mass of the Earth, and then you have some other object over here, little m, represents the other body. And there's a gravitational pull on them if they're close enough. But let's say that this mass is really, really, really far away. So we're starting at an infinite distance away. Now, if we were to calculate the amount of work to pull this all the way over here, so it's closer to here, we could do that using calculus. Now, we also know from class, work is equal to the change in energy. And in this particular case, it's only going to be changing in gravitational potential energy. So let's assume that there's a little bit of a force of gravity pulling on it here. And now, of course, as it gets over here, there's a much greater force of gravity. So the force of gravity is not constant. If we were to calculate the work done by that force of gravity, we can use the integral of the force of gravity dot dr, going from r initial to r final, where we know that the force of gravity is given by Newton's universal gravitational law, g big M for the mass of the Earth, little m, the mass of this object, divided by the distance squared. Substituting, we get this, and we'll say r initial, which is this distance all the way here, we'll say that is equal to infinity, and its final location here, r sub f, we'll say is just equal to r. So we'll set the limits to our integral as infinity for our initial and r for our final. This is a constant, so we could pull it in front of the integral, and therefore we're just integrating 1 over r squared. The integral of 1 over r squared is negative 1 over r, and we're integrating from r to infinity. And that will give you a result of negative g m all over r, because 1 over infinity is 0. This work represents the change in gravitational potential energy, which is essentially the gravitationally finally minus the gravitational initially. And you could say that our infinite distance, our gravitational initially, is essentially 0 when r is infinity. So in general, the gravitational energy at a position of r is given by negative g m and 1 m2 all over r. Hopefully that makes a bit more sense for those of you guys in calculus, and you can see how we actually derive the equation mathematically. So now you can go off to your problem solving.